Okay, so let's start with project management and decision analysis tools. The first thing that I wanted to mention is technology readiness levels. Here you'll see a diagram where it's kind of like a thermometer, where you start from TRL 1 and you go up to TRL 9, where TRL 1 is the very beginnings of a thought, so basic principles observed and reported, all the way to the most mature level, which is 9, where you have an entire system that is flight proven. So it's gone to space and it has demonstrated successful mission operations. So TRLs are a measure of maturity for technologies. And the way that we use them is we evaluate different TRL levels for different components. So we'll strategize about how to reduce risk or accept a certain amount of risk. To reduce risk, we'd incorporate higher level TRL components, subsystems, or systems. In your designs, you would investigate what the TRL level is for every single technology that you decide to use. So first questions that you should ask are, has it flown in space? Did it prove to be successful? What kind of testing has this gone through? What kind of environments was it tested in? So you'll see the reason why you ask these questions is because at some point, you're going to have to mature a technology from a concept to more critical characteristics. You'd have to physically manifest it into a component in a laboratory environment, and then something that's a more relevant environment. So a laboratory environment could be like a lab bench. A relevant environment could simulate certain dynamics. So it could be like a dynamics test bed on ground. And then it gets tougher where to have a prototype in a relevant environment, which could be like outdoors. If you were testing planetary surfaces, for example, then Hawaii has analog environments that simulate the moon and Mars. And then TRL 7 is the space environment where you just send it to space. It doesn't yet prove that the system works, but you have a prototype in space. And then TRL 8 is the system is completed through test and demonstration in space. And then TRL 9 is all the way, all the success criteria have been passed. So a question that I got, which was really quick to answer, is, was SpaceX's Crew Dragon mission an example of TRL 9? Yes, SpaceX's Crew Dragon mission successfully flew through space, docked with the ISS, and delivered astronauts to the International Space Station. So I would say that is successful and at TRL 9, which is very awesome and exciting. The next question I got, which I love this question, is there an average time or cost for technology to progress through these levels? And it touches on a nuance of the way that technologies progress through maturity. So there's something called the Valley of Death, and this is prevalent for technologies not only in aerospace. So you'll see here the TRL levels are on the horizontal axis, where you have the least mature technologies starting at basic research, and then again, the most mature where you have proven systems. So basic research is relatively easy for academics and government labs to do. There's generally some overhead associated with it, but most of that development is on paper or on a computer for analysis. And then we have applied research, which takes a little bit more money to physically manifest, but cheaper compared to something like a test in a space environment. And then a prototype in a relevant environment, as we were talking through the TRL thermometer, these tests can get quite costly in that the means to get there would take a huge budget. So you'll see here that there are many technologies in the very beginning, but technologies tend not to exist between TRL 5 or 6 because of this immense cost at that particular stage. where technologies are not yet profitable and you have to take a risk on and put a huge amount of money to get them to a state where it could be profitable. So I have a couple of perspectives from engineers at different phases in industry and also in academia. So here's a senior engineer at Boeing. He says, for many in the research and development community, a technology is generally proven when it reaches technology readiness level 6, at which point it has achieved system, subsystem model, or prototype demonstration in a relevant environment. And once proven, there should be no reason why the technology isn't available for use in every relevant application, right? Well, not really. In reality, there's a colossal distance between being technically proven and having a successful implementation. This difficulty in transitioning a new technology or approach is affectionately referred to as the Valley of Death. After TRL 6, there's a significant cost to mature the abilities of products and systems so that those seeking to use them can be confident that they will work as advertised. This cost and risk is the first part of the Valley of Death that makes it so hard to transition a new technology or approach to real life. Even if the risk is low that a new invention will work as intended, there's still an enormous amount of cost and risk before successful implementation on or as a product. So on the academic side, here's a perspective from Dr. Leitner of the University of Gothenburg. He says, university research in computer science largely falls into TRL 2, 3, and 4. In relatively rare cases, it might mature up to 5, but that's about it. Why do we not see our research through all the way until TRL 9? Well, there's no publications to do. You can hardly publish that you tweaked your tool, which you have already proven conceptually sound, to also work in a relevant demo environment. It's a lot of hard work with very little immediate benefit for the academic. Hence, people do not do it. Companies, on the other hand, usually do not want to touch anything below TRL 7 or 8. They may have research departments that operate on TRL 6, but those are few and far in between. Now, why is that? Simply because the risk-reward ratio is not right for them. Many of the academic ideas and lower TRLs might be sound in principle, but practical problems will still hinder their practical usefulness. Companies typically do not appreciate that kind of risk. It's obvious that there is a gap that prevents even good academic ideas from being picked up by practitioners. This gap is often referred to as the Valley of Death. It's the place where ideas go to die. This figure nicely illustrates why academics and people from industry often have such a hard time collaborating. Essentially, all parties silently assume that the other person will interface with them on a level where they typically start or stop. The academic assumes that the company will be willing to pick up their stuff at TRL 4, which they won't. The company assumes that they will receive technology on TRL 7, and this won't happen either. So yeah, everybody's unhappy and feels like the other person's not doing their job. Yeah, so I really love this question, and I think it's a little nuanced as to the way that science and engineering is done. Okay, so now we're going to go through all of the different documents in the template folder, which you'll have to copy and modify for your own use. So to give you the big picture before we dive into each type of document, the requirement verification and traceability spreadsheet that I have in the template folder offers a framework for the design. Like we talked about last lecture, requirements are the backbone of a good design. So you really want to spend a significant amount of time creating your initial requirements. And this may mean that you have to think farther ahead in the cycle of how are you going to verify those requirements? And those kind of thoughts can lead to refining your requirements in the way that, like, oh, if we were to do a test, then what kind of performance would we be measuring? Then there's something called a risk matrix, which I will go through today. And this is to ensure robustness in your design. There are things called system diagrams, which are a way to visualize the way components and interfaces are laid out. There are things called data sheets, which specify component interfaces and performance. There are things called Gantt charts, which offer a schedule. And then there are a suite of different budgets that keep track of characteristics to verify your requirements given your design. And budgets don't just mean money. In this case, there is an actual cost budget, which is a budget of money, but there are mass, power, data, and link budgets that we also keep track of. So the mass budget is controlled by the structures lead. The power budget is controlled by the electrical power system lead. The data budget is controlled by the command and data handling lead. And then the link budget is controlled by the communications lead. So those are documents that are required during the design process. And then after the design process, you have to come up with, integration and testing documents like mechanical integration slides, and then test procedures that all of your hardware and software has to go through. Okay, so let's get started. This is a template that is based around objectives, requirements, and then if you were to revise your requirements, also there's a tab for revisions, or columns for revisions. Here is the first tab, which has objectives. So last time we had presented on concepts of operations based off of your mission statement and objective. So what you want to do is put those in here, and you want to label them accordingly. Then what you want to do, if there are any revisions, then you want to put them here. So what the revision is, the reason why there's a revision, and then any sources that you drew that change from. You can also put in associated risks, and then your testing methods. All right, and then we have requirements. So here I didn't delete KAU's input here. So you can modify these as you see fit. But what I want you to do is go through your system and come up with that highest level. They're the mission objectives, and how do you translate them to system requirements? After the system, so you'll see here, each system requirement, the number hierarchy is here, where the highest level is going to be those first two digits. And then if it were the next level, so maybe a subsystem, then the next two digits. And then finally, the third pair of digits, that could be a component requirement, for example. Okay, so the spacecraft bus itself has system, subsystem, like EPS, and component, which could be like battery requirements. You can also have external requirements that come from, say, nanoracks or the NASA at CSLI requirements. Yeah, so you're eventually going to have to fill this in. And as the design process goes, there can be revisions to these requirements as you refine your design. And then you also would like to put the associated risks with each kind of requirement. And then we may not get to this tab, which is about implementation and status, but it will likely be that we play with this tab next semester when we have hardware. Okay. So I'm going to pause a second for questions. It's okay if you don't type it fast enough, just enter it in and I can come back to it. Okay, so next, the risk matrix. I will talk about risks later on in the lecture, and I'll go through an example. But just for now, know that there is a document that has all the risks and they are associated with a system, subsystem, or component. And then you have to answer these multiple questions. So what can we observe about the problem? How is this affected by, or does this affect others? And what's the problem we see? And then you start, that was the identification problem. Then you are evaluating the level of risk from that hazard in these columns. And then you're figuring out how to address those hazards given their likelihood of occurring. And we will go through these different tables, but very briefly, different hazards have different risk levels, where hazard is the actual bad thing happening, and then risk is the likelihood of something happening. And the combination of that tells you how important it is to address. So given red is more important, yellow is less important, and green is potentially acceptable, but you still have to keep an eye on it. Anyway, you want to address the reds first, right? Okay. System diagrams. So I have a small logistical thing to say about this. UH, I think, blocks this plugin for Google Drive. So if it turns out that you can't open this type of file, if you have a Gmail, it would be great for you to log into that. Just a quick debug thing. Anyway, so system diagrams are ways of representing the relationship between subsystems, or I think it's a way of showing a system architecture at different levels. So you can have at the system level, so for the Artemis CubeSat kit, I think you've seen this before, different subsystems, the different interfaces like data, voltage, or other kind of communication interfaces. But you can also have subsystem system diagrams where the components are laid out. So you can see that there are different levels of information that you want to display, and you just want to be clear about, you don't want your system diagram to be too congested. So it might be that you'll have to have a hierarchy of different system diagrams that you'll have to create. So I suspect that you'll have a system level diagram, and then for each of the subsystems, you'll have a system diagram. Okay. I wanted to show you this particular system diagram before we move on. So this is the command and data handling systems flight software, where different programs reside on the onboard computers and communicate across different data interfaces, which are labeled here. And then power is in red. So what I like about this system diagram is how specific component part numbers are labeled, like the temperature sensor, which has part number ADT7311. The programs are precisely named, like Agent Raspberry Pi gives commands on and off to Agent Switch, and also delivers images to Agent File. And data interfaces are explicit as well. So images, for example, is a data type, and on-off is a command type. Temperatures are a data type, so on and so forth. The components and programs are nested in their appropriate subsystems. So for example, the payload script is a program that resides on the Raspberry Pi Zero, and the Raspberry Pi Zero is a part of the overall OVC board. Yeah, so if you're ever thinking of sample system diagrams with the appropriate level of detail that is also aesthetically pleasing, you can refer to this particular one. Okay, so let's go back. data sheets. So I added a lot more documents into the template folder. You can navigate to it. This folder. But let's just look inside. What I should have said is all of the data sheets are separated by subsystem. So if you're looking for a certain ADCS component, you can go in there, and then we have all of, it's not totally comprehensive. There are some components missing, but say you want to look up the GPS, then what you should see is the data sheet for that particular chip with the different features like sample rate, the amount of time necessary for the sensor to cold start, the power draw, the size of the chip, so on and so forth. So these are really important in getting your component specifications and potentially also getting interface information, like the chip has different pins on it, and if you want to attach it to a board, then you need to know what the different signal names associated with the pins are. Yeah, okay. So that was just an example of a data sheet, and you can go through, when you're going through your mission design, that is the level of detail that you will have to go through. Thankfully, we have designed the platform already for you, so hopefully you'll just have to be thinking about your payload and how that interfaces with everything else. If you do want to make changes to the CubeSat kit, then you will probably have to look into these data sheets, into the components that your modifications touch, and just make sure that it's compatible. And if not, then you have to stitch the design together. Okay, so now Gantt charts. So the engineers in this group hopefully have seen Gantt charts before, but they're a way of keeping track of your schedule. You have different programmatic phases in a mission timeline. So for us, I would say that primary objectives or milestones are to have your PDR done and your CDR done. Then you can split tasks into, or you can split these major milestones into tasks and then associate how much time each task will take. And that should give you an idea of how long that program phase is. Typically it's the other way around, where you have all of your tasks and you need to adhere to a schedule, so you'll work backwards. You know that you have to have PDR done before spring break, so like, what do I have to do to get there? I can only spend this much time in, for example, researching this component and having it selected before I move on to the next thing that has a dependency on that decision. So yeah, you can see a sample Gantt chart here. It is by no means the only one or the best example. It's just something that you can refer to when you make your Gantt schedule. Okay, now the different budgets. So I've offered you the Artemis budgets. There is a breakdown here of all the different components that are involved in the kit. We have them all hyperlinked with their vendor, how many of them, the cost, the quantity. And this is important because your CubeSat kit, your CubeSat in general with the payload, has to fall under a certain amount of money. So I want your modifications and your payload to fall below $2,000. You don't have to worry about the Artemis CubeSat kit costs. That we already sunk those costs, so you can just take that on for free. But if you were to say add more components to the communication subsystem, and you're going to add to the payload, those costs you will have to consider in that $2,000 cost budget. So that is a design constraint. Okay, NAS. Here is a NAS budget, and we can all thank Evan for putting this together. Let's see. What do I want to say about this? Each subsystem has a certain amount of mass associated with it. Each CubeSat is limited to 1.33 kilograms. So we have about 575 grams for you to work with to add to the CubeSat kit. I will talk about this a little bit later. For power, we have all of these different components that are inside of the CubeSat kit, and they are separated by subsystem. They consume a certain amount of power and they are on or off during certain modes. So the modes are an initial startup, data collect, data processing, on and on and on. And we use this to calculate how much power or energy storage our batteries need to be at. And also for our power distribution system, we need to figure out what kind of peak power the power distribution system needs to handle. So yes, eventually you will be creating a detailed version of this where you're modifying the payload and potentially modifying the different kind of modes that you're having if this doesn't fit your mission. And then one of the labs later on in the class, you're going to have to do some kind of time analysis where each mode is on for a certain amount of time. So we'll get to that, no worries. Just know that this power budget template is here for you to have with the Artemis CubeSat components to work off of. Okay, there's something called a data budget. So just like the power system has batteries, the command and data handling system has memory storage. And then it has aspects like computation as well. So during the mission, there's a certain amount of data that the different subsystems generate that fill up the SD card. And it keeps accumulating on the SD card until you transmit the data back to Earth. So this is a way that we can make sure that our SD card does not overflow with data and we cannot store data when we need it. It would be very sad if the SD card filled and we haven't finished our science mission and our camera can't take another image because the SD card is full. So you want to also keep an eye on your data budget throughout the mission. Okay, for link budgets, a link refers to a communications link. So there are many different parameters that we'll read about in the communications chapter. But essentially this spreadsheet is trying to calculate if your satellite will communicate with your ground station and vice versa. There are many different parameters that you have to put into this spreadsheet, which acts like a calculator, such as, here is the instruction sheet. You can put orbital information into here, what frequency you are transmitting and receiving at, aspects of your transmitter and your receiver, characteristics of your antenna, what kind of losses you're going to experience. Losses prevent you from communicating, so you want to minimize your losses. And then there are all of these other tabs that you can tab through. And these terms will be defined once you get to the communication chapter, and creating a link budget will be the lab for that chapter. So please don't be intimidated yet. Just know that we have this as a resource for you. Okay. And then for integration and testing, I don't have any test procedures I want to go over, but I do want to show you a quick mechanical integration for you to get a better spatial understanding of how the CubeSat kit is put together. So every satellite, at some point after you're done designing it, you have to think about how you're going to put it together. And the order in which you put it together matters in the way of how easy it is to assemble. You don't want to create a design that is impossible to fabricate or assemble. So you do need to think about, if I were to build it, how would I do it? And that would get rid of any of those steps that would be impossible. So here we have the bottom plate. You put those threaded rods in, and then you put the structure around it, then the battery board. And then you have to install the deployment switches. So I'm just going to flip through, not really expanding on each step, but it shows you step by step how to put the satellite together. Woof, okay, that was a busy slide. Let's move on. All right. So we briefly touched on mass budgets and power budgets. So how do we even come up with the initial mass that you should allocate to your design if you don't have a design? So like, say you didn't have the Artemis CubeSat kit, how would you even pick a solution that was in the ballpark of where you want to go? So if you were to design a spacecraft from scratch, you want to have a rough target for how much mass should be allocated to each subsystem. Here are SMAD's guidelines in how to initially allocate mass in spacecraft. SMAD stands for Space Mission Analysis and Design, and it is the go-to textbook and reference book for aerospace engineers. And I have it here with me. This is the new SMAD. Quite thick and heavy. But as I mentioned in the preface, SMAD doesn't represent small satellites very well. So let's look at the closest analog that SMAD wrote about. They have a suggestion for satellites with no propulsion in low Earth orbit. They say that you want to allocate about 41% of your mass to the payload, and you'll notice that is the plurality of the mass. It has the most mass per subsystem, which makes sense, right? Like if you're flying a mission, it's going to be about the payload. The payload, the science is why we're in space. And then everything around it, the structures is allocated maybe 20%, then power is about 19%, and the other subsystems get a little bit of percentage in the whole thing. But if you look at the Artemis mass budget and compare it to what SMAD defines, our payload is just a baseline. I mean, you can add your own payload, and we definitely want you to. There's still 575 grams left for you to do so. But let's ignore the payload for now. The structure is about 20%, which is comparable to what SMAD said. And then what else is comparable? The structure, ADCS, and communications are on par with SMAD. But what you will notice is the power and computing system, so EPS, 48, OBC, 18%. Those subsystems are very significant parts of the small satellite and don't scale down very well. And the reason for that is that certain subsystems in spacecraft just don't scale at the same proportion from larger spacecraft. In this tissue box size satellite, you still need to have an energy storage system, and batteries are mass intensive things. I mean, if you look at like a Tesla car, for example, that battery is just lining the complete bottom of the car. That is the single most massive thing about the car. And you can make an analogy about that to the CubeSat. But you have to have a power system, so you have to include it. And then same with the onboard computer. Our Artemis CubeSat kit has 2 computers, so we could have minimized our mass, but we chose to have a very powerful computer on board and then a low power less smart computer on board to do the nitty-gritty things. Okay, you can also get a rough ballpark of how to allocate power in a satellite. So I have that for you here, where SMAD recommends for a spacecraft that, again, the majority of the power goes to the payload. And then here's the power allocation for the rest of the subsystems. What to say here? So again, the payload should consume the most power, but you'll note here that the next most powerful thing is the attitude determination and control system. This satellite is most likely assuming that you have active components in the attitude determination and control subsystem, like reaction wheels, which are like motors, and those take up a lot of energy. But for our kits, what you'll notice is that the ADCS subsystem does not take up much power, and that's because we have mostly sensors that draw very little power to get measurements. We don't have any reaction wheels or control moment gyroscopes. Instead, the Artemis CubeSat kit has quite a bit of power for the computer and the radio, and that's by mission design because, again, there are two computers, and for the communication subsystem, we are always trying to beacon because we don't have a pointing system. We don't have an antenna that has to be pointing at ground. It's just tumbling and like constantly beaconing. That's by design because our satellite is very simple. As we say, make it simple, stupid. Oh my gosh, I'm so old. Okay, so yeah, those are best practices when you're coming up with a mass and power budget without a spacecraft design, like without a baseline spacecraft. There are also things called contingencies, which I talked about in the textbook, but unfortunately I did not give you the initial step. So the mass budget, this is the initial mass budget you should use. This is the initial power budget. The contingencies are a secondary step once you have initial mass and power budgets. Over the design process, the spacecraft's estimated mass and power grows until those mass and power allocations converge to the final design at delivery. The overall spacecraft may be separated into the payload and the supporting spacecraft subsystems. So we build in mass and power margin as contingencies. We try to set aside mass and power so that when you encounter unforeseeable design changes that are necessary, you can execute on those design changes and not go over the maximum mass and power. The earlier in the process, the more we set aside. If you look at the JPL design principles, they suggest that you reserve 30% of the total flight system at the start of phase B, which is concept formulation. And then as you refine your design, you have less of that reserve that you need to keep around. So you can use 10% of the reserve while you're refining the design. And that iteration and that chipping away at the mass continues until you converge on a final design. What I want to mention here is that these are guidelines, these rows down here, but the Aerospace Corporation conducted a study looking backwards at the way that satellites and instruments were actually built, not just theory. And so these are their results where they looked at the final design and they looked at different stages of the design and compared how the final and initial designs differed when it comes to mass and power. And they actually saw that during earlier phases, the instrument actually needed quite a bit more margin before its convergence, but needed, less margin at CDR. Okay, and then the same kind of principle can be said about cost. Money budgets also have a margin designed into them in the design process. Say that we have $2,000, which is the amount of money we will be getting per team. The JPL design principles say to save 30% of your budget. So you would only plan to spend $1,400 on your initial design. And then as we go to CDR, you can again spend more of that money for unforeseeable design changes.